sextants here. When you pick up a sextant, you already measure your sine and cosine, not calculations measurements. What? No. Sextant's not measuring a sine and cosine. It's measuring an angle. Oh my gosh.
Yes, totally agree. It is measuring angles, not sine and cosine. But yeah, sine and cosine is just a relationship to angles. What happened to sextant doesn't measure angles, you know? Trigonometry.
He goes sin angle. I think he means sine angle is your 90-degree star measurement, aka GP. No, it's not.
So you're telling me to get your LOP, your line of position, it's not measuring the GP of the star to your location. Well, let's have citation that shows you otherwise. Using the geographical position and the estimated position, side reduction tables, will give you a calculated altitude from the estimated position, an angle for the azimuth, and from the estimated position to the geographical position. To construct a position line on your map or chart, an azimuth line is drawn radially from the estimated position. The position line is drawn at 90 degrees to the azimuth. It is drawn at a distance from the estimated position equal to the difference between the calculated and measured altitudes. If the measured altitude angle is greater than the calculated altitude, your actual position is closer to the geographical position than the estimated position, and the position line is drawn towards the geographical position. If the measured altitude is less than the calculated altitude, your actual position is further away from the geographical position than your estimated position. A contra-azimuth line is drawn from the estimated position at an angle equal to the azimuth, plus 180 degrees. The position line is then drawn at 90 degrees to this line. What did you just say?
Is your 90-degree star measurement, aka GP. No, it's not.
Okay, let's look at another one. This is the sun, GP, your circle position, and what do you know, distance from the GP. Well, it so happens that with a sextant it is very easy to measure the distance between our two spots, or measuring distance. The distance between your own position on the sun and the sun's GP is directly related to the altitude of the sun as measured by the sextant. That sounds a lot like trigonometry to me, doesn't it? The higher the altitude, the closer you are to the GP. If the sun were directly overhead, you would be right at the GP and very close to it, and our circle of position would be quite small. If the sun is low down on the horizon, you may be thousands of miles from the GP, and the circle position would be similarly sized. But either way, your own position would be somewhere on one of those circles. You can carry this step further by using one of the basic rules of thumb for celestial navigation. Subtract the measured sextant altitude from 90 degrees and multiply the result by 60, and that is your distance from the GP in nautical miles. For instance, if the sextant altitude is 72 degrees, as it might often be at midday in lower latitudes, you would be 1,080 miles from the GP.
Not calculation, and also it is already the angle toward the star, and also measured, not calculated. The cosine is your adjacent, aka 0 degrees, also measured, not calculated, with the measured angle to the star. No.
Before I show the sine and cosine relationship of a triangle, I just thought I'd show you this as well. Different lengths of a rope from the top of the maypole would produce different angles, which would correspond to distance from the GP. So far you're not sounding very bright, Mr. Mctoon. I remember posting a video about this a while back, but it seems Mr. McClown did not pay attention, so let's go back to using a sextant navigation school just for Mr. McClown. How to use a sextant. The sextant is a complex device, but luckily it is very easy to use. Basically, a sextant measures the angle between two objects. I wonder what those two objects would be. With at least one being celestial. Remember, never look directly at the sun. Obviously, you'll go blind. Okay, the user looks through an eyepiece and after adjustments sees both objects superimposed on each other. The measurements of the angle is then taken through the use of the two mirrors. The user looks through the sextant's eyepiece directly at the first object, usually the horizon, the one you guys try and throw away, There is actually a mirror in line of sight, but because it's only partially silver, the user can see beyond it to the horizon. The other mirror is connected to the movable arm and directs light from the second object, usually the sun and moon, the luminary, and reflects it onto the half-silvered mirror. The movable arm is adjusted until you can see both the first object, aka the horizon, and the second object, the star, moon, whatever. Then you read the measurements of that angle, the measured angle, located on the movable arm. The most common way of using a sextant is to measure the angle between the horizon and the sun. By knowing this angle and your local time, you can determine what your latitude is. If you also know the Greenwich Mean Time, you can also determine your longitude. And this just carries on from that page. I'm not going to read the whole thing through. I will leave links below in the description box just for you, but keywords to take here. Let's see, number 6. Now measure the altitude of the sun by reading the angle on the movable arm. That would be with trigonometry. And yes, you see they took about trigonometry and sextant and everything. So far you're not doing too well, Mr. McClown.
Your tangent is simply the 90 degree from here to the GPDU, all measured, not calculated. I think he's messing up SOHCAHTOA here. He's really messing up. I love it. Flatzoid. This is, you are real. I mean, you're coming out fierce on this.
Am I now? Okay, this is from the same teaching sextant work navigation. I suggest you read through it and then tell me again how I'm wrong, Mr. McClown.
And then another one here. This is so he thinks that celestial navigation, which he's never done. He thinks this is how it's done. He says, let's say you measure an angle of 25 and we know the GP is 90 to you. No, it's not.
Yeah, according to you, it's not. Although citation over and over from different sources tell different. Well, like I said, I'll leave all the links in the description box. Go ahead and read it for yourself, Mr. It doesn't involve triangles and triangulation, and then later you do say it does involve it. Now you're big backpedaling it back again and say it doesn't. You should really make up your mind.
But okay, so you assert. We know a triangle as the internal sum of 180 degrees on a plane, yes. So 25 plus 90 equals 115 minus 115 minus 180 is negative 65, not positive 65. You missed on that one. But that's fine. You should have had 180 minus 115. So points off for that. You're an adult. You should be able to get that. So what do we have? 3 angles, 25, 90, 65. Whoops. No, we don't. That's not how celestial navigation works.
All we've been seeing so far, Mctoon, is that you are the one that doesn't know how celestial navigation works. You might know the math to it, but you definitely are ignoring the principles to it, as shown with references and citation. Well, you've measured 3 angles, do the sine and cosine, voila, you do not need a globe earth for it. And this was exactly what Brian Leake was trying to explain to you, when he's trying to give you the equation of minus 90 and whatever, where you looked so confused. Because it was worked out on a flat horizontal plane, doing trigonometry, something you choose to ignore.
All right, I'll put up the picture. It's zero chance that he's going to watch, but I'll put it up anyway, just to be fair, because I am here to teach. So here we go. This is how celestial navigation actually works. You've got the one angle you're measuring between you and the star, which is line A. The star's at line A. And the horizon, which drops from horizontal, which is line C there, or angle C.
Okay, there we go. This is an actual worksheet from that you can fill in, Mr. Mctoon. You see, the dip is just a belief that the globe is dipping down, but in reality no one's eyes are embedded into the floor, our point. And exactly where you guys say, oh, the horizon doesn't matter, aka why you have bubble sextants. Of course it matters, because you are pushing the horizon up to your horizontal. You understand? To have a horizontal reference, because your eyes are not embedded in the ground. It's simple as that. So yes, you are creating a horizontal reference. You're taking away your so-called dip, but it's reality, your eyes are not embedded into the ground. So it's simple. Your C angle you're measuring is you that's above the horizon, the horizontal base, which you are still proving you first need to have your horizontal base to be able to do your measurements. Okay, why you guys have to throw away your curve to make the measurement in the first instance. Now this one is showing without refraction. Let's show one with refraction, just so you guys can have all your little corrections made into it. Okay, well there you go. Refraction of the atmosphere. So they're using standard refraction, obviously. You see how the apparent position and the actual position, well, you can go through it and you can fill it out and do as you please. Just realize that you're using a trigonomic function, triangulation, using triangles on a horizontal baseline, which you're saying you're not doing. So, are they teaching everybody wrong, Mctoon, or are you maybe teaching everybody wrong based on your belief that you do not need triangles and triangulation?
Anyway, you measure all of angle A. I didn't label the lines. I should do that. Then you subtract off the angle C, which gives you angle B. That angle B is the one that you use in celestial navigation. One single angle, not a triangle. 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 One single angle. And you'll see there that bottom line that's parallel to line A, that's the GP to the star. There is no triangle between you and the GP of the star and the star. There's no triangulation in celestial navigation. 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 Nowhere. Nowhere at all, Flatsoid.
I'm just going to play this clip from Toon.
When Mitchell from Australia and Mr. Sensible were going back and forth, they kind of both had a point, because it seems like there's you could do it using both methods. Would you agree with that?
No. There is no triangulation in celestial navigation. It's about it's about the distance and about the angle to the GP. So you can draw it on your chart, draw a line there, and then you do it for all three, and you get your intersection. So it is actually triangulation. You can draw a triangle, solve the triangle, and know the angle that the light, or that the object, must appear to be. And so we can do triangulation, but we have to presume that the Earth is flat. But if you're doing triangulation, you do a triangle on the surface of flat Earth, presuming flat Earth, you get then
hello everybody. This is unusual.
Sorry, that was the video from Flat Earth Math that I clicked on and it started playing. So yeah, I don't know.
It just seemed like a very awkward ending there when he realised what he was just saying, that he has to presume the flat Earth and draw the triangle on that flat Earth. Triangulation actually does work. Very, very awkward.
Indeed, he's conceded the point. I just wanted you to point that out, Mitch. Indeed, that's a concession. Yes, you have to have a flat Earth to acquire an elevation angle. As Toon found out 78 times, we're up to now, by the way, if anyone's keeping count. You can't first measure an angle if the surface is curved. No, you need a flat baseline. Game over.